Okay, good afternoon. And yes, it's me, Daniela Ferretti, and today I will present you I will do the tutorial of isobaric labeling. Christopher will present you the theory behind it, and now we will do the tutorial. If you see the program, you can see that there are two slots, so one here and another one after the coffee break, because we will do two separate tutorials. One in one specific topic now, and another one after the coffee break. Before to start, I would like to say something. So you will see that I will show you through screenshot, because this tutorial, compared to the tutorial that you saw during the morning, is not only on, done in Perseus, but we will go from MaxQuant to Perseus. So I will show you how to run the isobaric labeling from MaxQuant, then get the output, from the output, then analyze in Perseus. This one I will do that through slides because I tried last year to do this one in practical altogether, but we realized that it was too long to do both of them in 1 hour. So we prefer to keep for now the slides so that you can go together, see the workflow together with me or what I apply. But don't worry, you have all the data, MaxQuant output, Perseus session, MQ part file in the USB drive. And together with that one, you have also the PDF. So it means that all the steps that you see now, there is actually, it's more detailed, that exactly each button that you have to press in a way to do exactly the same process. So we will start now with the first tutorial. First, I would like to highlight what is new in isobaric labeling in MaxQuant. So already Jürgen on Monday already introduced this. So first, since last March, we have finally the TMT correction factor done properly. So developed, defined properly in MaxQuant for the TMT Pro, so 16-plex and the 18-plex. And we have also finally the TMT frames for MS2 and MS3. So now you can finally upload your raw data with these multi-voltage frames also for TMT MS2 and TMT MS3. It was already available with LFQ, but it was not available for the TMT, but now, yes. And so these are the new two things, but as tutorial today, I will go to an example to how to run a data set that it has some correction factor from MaxQuant to Perseus, as I said. And then later, after the coffee break, we will see exactly the application of this PSM weighted normalization. So it means that I will not show you for today how to run a dataset in TMT frames. I will do it at the end of this tutorial just to show you which is the parameter that you have to change compared to the other quantification, because it's not so that different. All the rest is not so that different. You will define the plex as usual and so on. However, we will have soon also a paper about that. So there will be also there together with the paper, the supplementary material that it will show you exactly how to do these TMT frames in MaxQuant. So let's start with the TMT correction. As I said, so already Christoph introduced you the concept, the theory concept behind. So when you have your reagent kit, you receive also with the reagent kit this reagent batch kits. So you have your the correction factor that you have to apply for the kit that you have. This correction factor, there are just exactly the adjustment that you apply in your reporter ions for exactly removing one of the disadvantage of isobaric labeling, like the isotopic impurities. This, let's say, kit is exactly like in this screenshot. This is one example that I just took it from the website of Thermo Fisher, but there are many of them. And this one exactly depends on the kit that you have that you use. The idea is that now today I will show you exactly that you have this kit, how then you do that in MaxQuant and then Perseus. And to do so, I would like to take an example exactly from a paper. Why? Because until now, also in the previous summer school, what we will usually do is that I'm giving you some raw data, whatever these data are from. We don't explain the experimental design in the tutorial, but we prefer to start this year to exactly tell you from which paper we took this data, see the experimental design, and then from that one tell you the goal, let's say, that we have for our tutorial. Because of course, this is, for example, the paper that we use now, but we will not go through to all what they did in the paper. This one will take otherwise 2 hours at least together. But I will take this example to show you exactly how to apply this correction factor to see if this correction factor really are useful comparing the raw your raw reporter ions versus the corrected reporter ions. And this is an example. So this is a paper where they use the correction factor. So they have their reagent kit where there was the correction factor. And in particular, it was an isobaric labeling. It's MS2. TMT Pro 16 plex, and so in this 16 plex there is one the first channel that is the carrier proteome channel, then there is the second one that is just an empty channel, and all the others are the single cell channels, so our sample channels. Before to go more in specific, so here we have the first channel that is the carrier proteome channels. Nikolai Slavov already introduced last Tuesday what is a carrier proteome channel, but I would like just to add that don't confuse the carrier channel to the reference channel. So the carrier channel is something different compared to the reference channel. And also you can see exactly from this paper that exactly also Nikolai Slavov published together with the others, the protocol that you do that in a way to do the reference channel and the carrier channels. So you can see from here that it has a different final concentration for the carrier proteome channel, and also the concentration of the reference channel is completely different. Because the idea of the carrier proteome channels, exactly as Nikolai Slavov introduced last Tuesday, is that to make a better peptide identification. Differently, the reference channel, the idea of the reference channel is a way to control the technical variability in your analysis, that then you will use this reference channel to normalize your data. And this reference channel, it's exactly the example that then we will do that in the tutorial after the coffee break. So we will see exactly in another experimental design where there is this reference channel, we will see how to use it. But here, in this case, we have a carrier channel. And also, you can see also from the screenshot that the TMT labeling reaction, that also here, you don't see that the carrier channel is confused with the reference channel. You will see that one of the channel is a carrier one and the other one is a reference channel. So please don't confuse these two when you read any other paper around. So we have this carrier channel. Finally, we have an empty channel, then we have the sample channels. What we have also here for this experimental design is that we have sample channels that are across species. So we have mixed species samples. So where we have different ratio across these sample channels. Okay, across the sample channels, and there are different ratio across these three species: yeast plus E. coli, and then human. So it means that we need also to take this one into account when then we process this data in MaxQuant. It is something that also they introduced you last Tuesday during the tutorial in MaxQuant, but I will show you also once again how to do that when you have exactly these several species in the same data set that you use, because there are these different ratio. For that reason, so we have this data set, and in this one, again, we have also the correction factors. So we have our reagent kit. The goal The goal of our tutorial is that in MaxQuant, exactly to how to run this TMT data set and editing the correction factor, and also apply this to do that one across the species, and then to do that, take the output that we get from MaxQuant, do that in Perseus, and exactly see if first MaxQuant did it properly. So if we see exactly if this correction factor were applied, and how we do that, we compare the raw reporter ions versus the corrected reporter ions. Let's start with MaxQuant. So the first part. So first, as usual, we load our data. So if you go to this paper, the raw data are available. It's in a public repository. You will see that there are more raw data. Here you just see just only 2, because in the USB drive, we upload only these 2, because to upload all of them, it takes a big size. So in the USB drive, that one you can do that whenever you want, if you want to use specifically this data set. So these 2 raw data sets is just for you as to give you an idea of how to run the data set. But if you want to do that completely across all the carrier channels and all the across all the species, please have a look to the paper. And with this one, there is the PRIDE code repository, and there you will find all the raw data. So we load our raw data. We define a specific set of experiment, as you can see here. What I usually suggest is that keep, if they provide a metadata, that one is already difficult sometimes to find, but if they provide a metadata, please set the experiment in the same name labeled as it is in the metadata, so that whatever you did, it may be something wrong or not, you can go back and see what it was not done properly. So that is just my personal suggestion based on my experience. Sometimes, unfortunately, I have to say that sometimes the metadata is not provided, unfortunately. Sometimes you find in the supplementary material of the paper, the best will be that you have in the repository, in the public repository, but unfortunately, it's not always available. As far as we know, the PRIDE community, or better, the EMBO community, they are working on that in a way that you can provide a standard experimental design, what they also call SDRF, in a way that everybody, whenever you publish a data set, you will follow that metadata, and everybody can read what you did, and everybody can reproduce it properly. Because until now, unfortunately, sometimes it's not so that easy. However, then we have our raw data. We have this raw data. Now let's go to the quantification. We saw in the previous slides that we have a MS2 16-plex. So what we have to do is that we have to go to the group-specific parameters. Here in this case, yes, we have only one group because it's only in this quantification TMT MS2, and we say that it's MS2. So we go to reported ions MS2. If it was MS3, it was reported ions MS3, of course. And then we say the plex, that in this case is 16-plex. As you can see, when you press the plexes, MaxQuant generate this table where exactly you can define your correction factor. By default, it's completely 0, because MaxQuant doesn't know which are your specific correction factor for your dataset, but the idea is that you can set up as you prefer. How you can set up this one is that you have, first, there is one option that you select each of these of the channel, you edit, you press the button edit, you will open a new window, and there you will just type exactly the correction factor that you have in your reagent kit. And this one for example, for the first channel, this one, then you go to the next one until the 16 one. But you can already see that through the years, we moved from 6-plex to now we have 18-plex. I know, probably next year we will have even more plex. Let's think about that. And so what it means is that for each of them, each time you have to go press edit, and once again. For that reason, what we want to do is that you can do that like that. So you can edit each of them, and then you will have your correction factor applied. But what we also define is that you can do a template. So you have MaxQuant, you set up, you say the quantification MS2, you press the plexes, but then what you do is that you export the table that is just simply a TXT file that you can open in Excel, and then through that one, then you can change it as you prefer. After that, you will just import it, and then it will MaxQuant will read this one. In this way, you don't have to set up for each channel manually in MaxQuant. You can do that directly in Excel. And also, let me also say, you always save your reagent kit also in the same folder that you have in your dataset. Let me also say that when you save this the MQ part file, so the session in MaxQuant, MaxQuant will also save this correction factor, so how you edit. But let's say if you have also the template in addition, external exported is always good for you. No, maybe you have now a specific reagent kit, and no, after 2 weeks you use a different one. You can store all these correction factor in a separate folder, and you have them listed in addition together with the MQ part file provided by MaxQuant. We can also provide sometimes, we are thinking to also provide some batch effect automatic. So maybe you can select a specific one and then MaxQuant will fill it, but we can do that for some of them. But unfortunately, the reagent kit change all the time. So it means that we should have one employee at Cox Lab that will do every week this one and check from Thermo Fisher or each batch that we should fill all of them. So we can do that. We can prepare some examples for you, but I would say that the best idea is exactly that if you set up your template, then you can manage as you prefer whatever the reagent kit you have. So we define our quantification, we define our correction factor, great. And now we go to the database. So we saw the experimental design, and we saw that we have an experimental design across species. So we have different species. So that means that we have to include in MaxQuant for each species the FASTA file correlated to this one. So just download on UniProt the specific database for that organism. And we saw that there were 3. And here you see that there are 3 FASTA files, so exactly the corresponding one. But how MaxQuant then recognize that you included 3, and you want to see exactly this data set across these species? What you have to do is that what you see here on the left side is that you have to go exactly in the global parameters in the identification, press this checkbox and say that, look, I want that you do that, you read this database across all, you do the identification across all the database, but you filter based on the taxonomy ID has to be filtered based on the species. So that MaxQuant will recognize, okay, you have different species, and now we'll do this identification, but I will, let's say, keep in mind that you have for each database. So we'll see the difference across these databases, so across the species. This is already enough. So what then you will do is that just press the bottom start, as you saw last Tuesday, and MaxQuant will process. As they already told you during the tutorial, just keep attention in the number of threads that you will set there. That one, it depends on the memory that you have, your server or AWS or whatever you use. Just have a look at that, because for each thread you need, for a DDA TMT, you need for each thread 2 GB of the memory RAM. So if you have a memory RAM, I don't know, as just basic sample 80 GB, 40 threads. Okay, we did it MaxQuant. So this is how we will process. MaxQuant will process, and as usual, we will process and will give you an output that will be in the combined folder. Under combined folder, the TXT folder, you will have the output tables, what Carlo showed to you yesterday. In this one, then you can start to analyze. You can start to analyze in Perseus exactly as Juan presented to you this morning. And I will show you how to do that exactly with Isobaric labeling. So now we go through the tutorial in Perseus. In Perseus, so what we will take is the ProteinGroups TXT file. But here you will see, exactly from this one, you will see this reporter intensity corrected and the reporter intensity. Which is the difference is that the reporter intensity are just the raw reporter intensity. So even if you put in the correction factor, for the reporter intensity, MaxQuant will not read it. It's something like for him, it's 0 for the reporter intensity. But for the reporter intensity corrected, it's exactly where MaxQuant adjusts your reporter ions based on this correction factor that you included in MaxQuant. our idea, the goal of our this tutorial it's already to see if we see a difference between the raw and the corrected. So what we will do is that we will import both. So we will import the raw one as well as corrected. So you will select the corrected one, so the reported intensity corrected, a reported intensity, and you will select as main column. And you will have it in Perseus. What we need to do now is that we need to tell exactly the experiment that we have in our in the experimental design that we have in our data set. Okay, like here, for example, we need to tell if we imported the reported intensity default that are the raw one and the reported intensity corrected, we need to create an annotation to tell to Perseus that this one are the raw one, this one are the corrected, and then also say the labels and the carrier levels exactly as is written in the experimental design. This one, you can do that already. Juan should show you this morning as an example, but you can do that manually in Perseus. But again, also here you can create a template. So it means that you can export the annotation and then change it in Excel and then import it once again, like here in this example. So you write a template file, it generates what we call the group.txt, but you can rename it as you prefer. You can go to Excel, you can include as many annotations as you want. So the column B, it's one annotation, column C will be another one, D, another one again, and so on. And then you will read it. It will be read it from file. You will read this file and you will import it. And then you will see, like exactly you see here down, you will see exactly this each column that it was the column B, C that you see in Excel. Now you see exactly as annotation here. And actually you also take, as you can see, also the name that you gave it to the columns in Excel, so that you can identify each annotation, what was it. So, okay, like the carrier, the label, the replicates, and so on. Okay, so we said that in this case, we have across species, okay? And we saw that we integrated multiple FASTA file and we tell to MaxQuant that he has to identify the difference across them. But when you do this, you will get one output, so one protein.txt. How now you can identify if that protein groups is referred to that database or to the other one? You can do that checking in the protein groups file what is called the taxonomy ID. That in that one it will be written exactly the name of the organism that you use. So taking taking just an example, like here you have Homo sapiens and yes, eukaryosis. Yeah. So you have these two. So this one are the two that are listed in this column as a categorical column in Perseus, but as a categorical column in the protein groups TXT file itself. What you will do is that you can, for example, for our cases, we want only to take the one that are Homo sapiens. So we will take only the Homo sapiens. So what we will do is that we use the filter based on categorical column. We will take this species and we will filter and take only the Homo sapiens. Just be sure that you click in keep match rows. But you can also stay focusing also in another database. For us, because we followed following our experimental design, reading the paper, and for checking exactly this difference across comparing the raw and corrected, we decided to go for this tutorial taking only the Homo sapiens. And specifically, what we will do is that for now we have only the human Homo sapiens, but what we will also do is that we will take only specific channels in a specific carrier level. Specifically, we will take these two, so we will compare the first, yes, two channels in log2, okay, and these two specific carrier. But you can do that with all. So also the paper will show you that you can do that with all, just you have to combine many times in Perseus the combination to do this distribution, the ratio, log2. So I took these two examples, but you can do that exactly for all carriers that you have there. In a way to do this, what we do is that first we select the label that we want. And you can see from the experimental design that we need the 126, 130, and 127. So what we will do is that we will filter our matrix. We'll do that we basically taking the filter columns. We will take the labels that we define in our annotation rows, the template that we defined before, and we take only the ones that we need for this example. And we take these three, exactly the one that I said before. So the 126, 127, 130. And again, keep matching columns because we want only that one. We don't want to remove, but we want to remove all the others. Okay, together with that one, we need also to filter our output, the protein groups file, taking only specific levels, because as again we want to also only for this tutorial take two specific carrier levels, and we say that we will take these two, the 210 and 434, and again you have to keep matching columns. So it's similar again, once again, to do the same process, just filtering to see the difference of this. Okay, so now here what we need to do, we need to see the ratio. So the ratio that it was here. So we need to reproduce the distribution log2 channels using these two channels. Okay, if I do the log2, automatically the ratio will be x minus y. Okay, if I do the linear, the ratio will be x, the ratio divided by y. But because this one, it was log2 transformer, we just do the subtraction. So it means that here, in basic, combine the main columns, so because we need to take these two specific channels to combine them to apply an operation that for us is this subtraction. We will combine the two specific reporter ions, these two reporter intensity, to see exactly the difference. We have to do this one for these two specific carrier levels that we already filtered, fine, and for these specific channels. However, we have to do this one for the raw one, so for the reported intensity, and after when we're done with the reported intensity, the same procedure also for the reporter intensity corrected, because we want to compare this one. So what we will get as output is that we will get for the log2 126 and 130 and the carrier level 210 one distribution with the raw one. For the same one, another one with the corrected, so two for each carrier level, and for the 434, the same distribution with the raw one, and then again with the corrected. So in total, we will get 4 distribution, 2 from the raw one and 2 from the corrected. How we do that? So we do that one, we calculate that one for each combination. So it means that we do the combination for the raw one, for the corrected twice. So 4 times we do this procedure of combination. What we will get as output exactly the calculation in the matrix. So we will get the subtraction of the two columns, but we want to see the results. So how we see the results is that we have the visualization section in Perseus, and that one I already showed to you in this morning, and that one we will do that using the profile plot. The profile plot will do that line plot, so connecting the protein groups that you have across the log2 distribution that you calculate. But you can also define here in Perseus the box plot. So you will have the line plot, but you can also additionally visualize pressing the logo box, the box plot correlated to the distribution that you have in the distribution of the combination that you did. And you can see from here that you see exactly a difference. So the first one this one, so the first line is the carrier level for 134, the raw one, and the second one is the same one corrected. And then you see the raw one, 210, and then you see the corrected, and you can see exactly that difference. You can check it comparing this one to the paper and to the results of the paper, because these are exactly just two carrier level that exactly they show in the paper, and you will see that you will get exactly the same results. And this one proves that you get different, your correction factor worked, but most important that MaxQuant Atlas, let's say, correct your data correctly using the correction factor that you imported. So this is how it works, the correction factors. So as you can see, it's very basic. You just need to be careful to read the experimental design, because all the rest is very just combination of different reporter ions that you have. But in addition to that, before to finish this tutorial, I would like to spend just a few minutes to show you, in case you have a TMT FAMES out, what you need to change compared to the configuration that I showed you before. So in TMT FAMES, the same will be, okay, you have your raw data. In TMT FAMES, you will do the database. So you will use the FASTA file based on the experimental design that you have. But in quantification, so you will tell the plex that you have. The only difference is this one, that when you go to the group-specific parameters in type, instead of selecting TMT reporter MS2, if it is a TMT MS2 FAMES, you will select FAMES reporter MS2. If it was a TMT MS3 FAMES, it means that you will select, and it's listed, the FAMES reporter MS3. All the rest in the process of MaxQuant is still remain the same, so there is no changes to do that. Just follow the experimental design that you have. And that's it for this tutorial. As I said, then later we will go to the PSMS normalization after the coffee break. And once again, I'm sorry that I show you through screenshot, but again, we spent time in preparing the tutorial so that you can go through each step after the summer school whenever you want and reproduce this. So, and plus you have also the PSMS session for that. Thank you.